All right, let's talk about NVIDIA. We all know them now as this absolute giant, the company basically powering the entire AI economy. But here's the crazy part. That was never the plan, not even close. This is a story about how an empire got built, yeah, but it was built by accident, and maybe more importantly, out of pure desperation.
So you gotta ask, right? How in the world did we get here? How did something that feels, well, kind of frivolous, like video games, end up building the literal foundation for the AI revolution? The answer isn't simple. It's not a straight line at all. It's a story packed with mistakes that almost killed the company and some of the most brilliant pivots that honestly changed computing forever.
I mean, just look at this. On one hand, their entire reason for existing was to make video games look prettier, to render those 3D graphics. And on the other hand, what are they doing today? Oh, just powering a global technological revolution. The journey from point A to point B, that is the real story.
Now, a lot of people will just chalk this up to luck. Oh, they were just in the right place at the right time when AI blew up. And sure, there's an element to that. But the real story? Oh, it's so much more complicated. And honestly, it's way more interesting. This isn't a story about luck. It's a story about survival.
And to really get how they succeeded, we have to go all the way back, to the moment they almost completely vanished. Seriously, their entire identity, their whole DNA as a company, was forged in the fire of near-total failure.
So picture this. It's 1993. NVIDIA is brand new, and they're jumping into a market that is just brutal. There were over 24 other companies all fighting for the same thing. And what do? By 1995, they launched their very first chip, the NV1, and it was a complete and utter disaster. Just 2 years after that, the company is literally staring into the abyss, facing total financial collapse.
So what happened? What went so disastrously wrong? Well, they made a massive bet on a new technology, and it completely backfired. It's like they decided to build a revolutionary new car, but they made it run on a special fuel that literally no one else in the world used. That's what they did. Their chip used these elegant curved surfaces to draw things, but the entire rest of the industry, pushed by Microsoft, standardized on using simple triangles. Poof! NVIDIA's tech was suddenly incompatible with everything. Their big bet was obsolete, basically overnight.
And we're not talking about a minor little hiccup here. The company's CEO, Jensen Huang, said it himself. We were 30 days from going out of business. 30 days. That's how close they were to the edge. And that moment, that insane pressure cooker of a moment, it became the foundation for everything they would do next.
Okay, so their backs are completely against the wall. They have to do something radical. And this is where the story gets really good. Because their desperation didn't just save the company. No, it created a whole new way of doing business. A new formula that would eventually just crush their competition.
They called it the brutal pivot, and man, it was. First, step one. They had to completely abandon their own tech. You know that fancy curved surface thing they'd bet everything on? Gone. Threw it in the trash. Step two, they had to embrace the standard, triangles. That meant starting from scratch, re-engineering a whole new chip with the entire company's survival hanging on this one single launch.
But here's the thing. They didn't just change their tech. They changed their entire company's metabolism. They committed to this relentless, almost impossibly fast 6-month product cycle. Think about that. That wasn't just a deadline. It became their entire culture. A brand new chip with new features, better performance, every single 6 months. It's insane.
And you can see just how nuts this was. Look at their competitors. Guys like 3DFX and ATI, they were working on a 12, maybe 18-month cycle. NVIDIA was moving 2, sometimes 3 times faster. It's like they were in a sprint while everyone else was taking a leisurely stroll. This crazy pace meant they could innovate so fast, they just left everyone else in the dust.
And the result of all this? Their comeback hit, the Riva 128 chip, was a monster hit. A massive success. It was fast, it was compatible, and most importantly, it saved the company. They sold 1 million of them in just 4 months, and that gave them the cash infusion they desperately needed to keep that insane 6-month sprint going.
So, the comeback is complete. They're back from the dead. But NVIDIA wasn't just going to focus on speed anymore. Oh no. They were about to make a fundamental shift in how computers even worked. And to do it, they came up with a whole new name for their creation.
So in 1999, NVIDIA drops the GeForce 256, and they call it the world's first GPU, the graphics processing unit. And listen, this wasn't just some slick marketing term, it signaled a massive technical change. Before this, you see graphics cards were just kind of dumb. They were pixel pushers. Their only job was to color in the dots on the screen. But the GPU was different. It was becoming its own powerful, independent brain.
Okay, so here's the crucial thing to understand. Before the GPU, your computer's main brain, the CPU, had to do all the heavy lifting for 3D graphics, all the complex math, the geometry, the lighting, all of it. The graphics card just kind of colored in the picture afterwards. But the GeForce 256, the first GPU, it took all that hard work and put it directly on the graphics chip itself. And that freed up the main brain, the CPU, to do other important stuff like game physics or, AI.
And the performance jump? It was absolutely staggering. We're talking 10 million polygons a second. For game developers, that kind of power was a complete game changer. It let them build worlds that were way more complex, way more realistic. This was the moment the GPU truly became a computational powerhouse. And this is where it all comes together. The final, most important piece of the puzzle. Every single one of these decisions, the brutal pivot, the 6-month cycle, inventing the GPU, it was all done for one reason, to make video games better. But in doing so, they accidentally, inadvertently, created the perfect tool for something else entirely. So here is the absolute core of it all. To draw a complex 3D scene in a video game, you have to do thousands, millions of little calculations all at the exact same time. That's called parallel processing. And it just so happens, by a beautiful, incredible accident of history, that the math behind artificial intelligence also relies on doing thousands of simple calculations all at the same time. The exact architecture they built for gaming turned out to be the perfect architecture for AI.
And this quote just nails it. For years, NVIDIA was basically smuggling a supercomputer architecture into consumer gaming devices. Think about that. They were sneaking these incredibly powerful parallel processors into millions of regular PCs, all disguised as gaming cards. They built this huge foundation for high-performance computing years before anyone even knew what the killer app for it would be. It was the ultimate Trojan horse.
How did a piece of hardware designed to do one thing, make video games look amazing, secretly morph into one of the most powerful computational tools on the planet? To get the answer, we have to rewind the clock a bit. Okay, so let's go back to the early 2000s. Graphics processing units, or GPUs, had a really big problem. They were these incredible powerhouses, but they were also incredibly rigid. They were built for one job and one job only, and that created this massive traffic jam, a huge bottleneck right inside your computer case. The issue was something called a fixed function design. The best way to think about it is like an old-school factory assembly line. Each station can only do one very specific task, and they can't help out the person next to them, even if there's a pileup. The silicon itself was literally hardwired to do specific jobs, and you absolutely could not change it. So that assembly line was basically split into two teams. First up, you had the vertex processors. Their whole job was to handle the 3D geometry, the skeletons of everything you see on screen. Then you had the pixel processors, and they came in and painted those skeletons with all the colors and lighting. The big problem? These two teams couldn't help each other out. Ever. And this is where you really see the inefficiency. Imagine a game scene with a ton of complex shapes, but really simple coloring. The vertex processors would be totally slammed, running at 100%, while the pixel processors were just sitting around twiddling their thumbs with nothing to do. It was a huge, huge waste of potential power. But here's the twist. While gamers just saw a bottleneck, a handful of really smart researchers saw something completely different. They saw raw mathematical potential. They realized that deep down, a GPU was just a ridiculously fast math machine, and they started figuring out these clever and frankly bizarre ways to hack it for science. And when I say bizarre, I am not kidding. To run a scientific calculation, they had to disguise their data as red, green, and blue color values for pixels. Then they would trick the GPU into thinking it was rendering a picture when it was actually running their equation. And finally, they'd have to read the colors from the final image just to get their answer back. It was insane. Someone from back then described it perfectly, saying it was akin to building a ship in a bottle. I mean, how great is that? It was a cool technical stunt, for sure, but it was just excruciatingly hard. You couldn't build the future of science on a hack like this. it was a dead end. The real turning point came from academia. A Stanford PhD student, a guy named Ian Buck, created this kind of translator called Brook GPU. It basically handled all that crazy pixel math behind the scenes so scientists could just write normal code. It proved a much better way was possible. And NVIDIA, they weren't just paying attention. They went and hired him. And this right here is where the story takes a dramatic turn. Armed with this proof of concept, NVIDIA decided to make a massive, incredibly risky bet that would honestly change computing forever. The year was 2006, and NVIDIA was getting ready to launch a new product that was so radically different from anything before it, you could argue it was the single biggest gamble in the company's entire history. Their solution was called the Unified Shader Architecture. What did it do? Well, they completely threw out that old rigid assembly line. Instead of having separate specialized teams, they created one giant pool of flexible general-purpose workers that could handle any task you threw at them whenever it was needed. The chip that made all this possible was the G80. It got rid of that fixed pipeline, it had 128 of these flexible units, which meant no more idle silicon. The chip could balance any workload on the fly. And this is critical. It was built to handle the kind of small, individual calculations that scientists need, not just the big blocky ones for coloring pixels. It was designed for science from the ground up. But here's the thing. This revolutionary piece of hardware was basically a locked treasure chest. It had all this incredible power inside, but nobody knew how to open it. So NVIDIA had to create the key. So you have this amazing new piece of hardware, the G80, totally ready to change the world, but that hardware on its own, it's a locked box. The key was the software, a platform called CUDA. You see, without CUDA, the G80 was just another fantastic gaming card, but with CUDA, it was a full-blown revolution. CUDA was a game changer because it let developers completely bypass all those old clunky graphics languages. For the very first time, they could write code in a language they already knew, C, and run it directly on all those powerful parallel processors. It made the immense power of the hardware actually accessible to normal people. And this brings us to NVIDIA's absolute masterstroke. It wasn't just about building the technology, it was about the brilliant way they got it into the hands of millions of people, without them even realizing what they truly had. It was a perfect Trojan horse strategy. Here's the core of it. The GeForce 8800 GTX was marketed and sold as the ultimate gaming card, period. Gamers bought it in droves to play games like Crysis. But what they didn't know was that hidden inside every single one of those cards was a CUDA-capable supercomputer just waiting to be activated. And the result was just staggering. Overnight, there were millions of these incredibly powerful devices out there in the world. A computer science student no longer needed access to some $10,000 workstation to learn parallel computing. They could just use the gaming PC they already owned. NVIDIA instantly created a massive, built-in army of developers for its platform. This table just lays out the competing philosophies perfectly. While competitors like ATI, who later became part of AMD, split their focus, they sold different cards for gaming and different cards for professional work, NVIDIA put everything into one single unified product. Their tightly integrated hardware and software approach with CUDA just worked, while the more open alternatives struggled to gain traction. And this marked a really fundamental shift in how computers are built. For decades, it was always hardware first, and then the software had to adapt to whatever the hardware could do. With CUDA and the G80, NVIDIA completely flipped the script. For the first time, they were designing the hardware specifically to serve a software idea, the idea of massive data parallelism. What does it take to survive when you've poured billions of dollars into an idea that feels like it's from a different decade? Well, the answer is pretty wild. It turns out NVIDIA didn't survive by winning over the big guys or convincing the mainstream they were right. Nope, they survived by finding allies in the most unexpected places. We're talking fields that had absolutely nothing to do with their main business. Okay, so let's set the scene. We're talking about the years between 2007 and 2012. NVIDIA has just rolled out this thing called CUDA, their big platform for using GPUs for more than just games. You'd think people would be excited, right? Wrong. It was met with, well, a ton of skepticism, and it put the company under some serious financial heat. And you have to understand there was this huge disconnect happening. The market, Wall Street, they all looked at NVIDIA and saw one thing: a gaming company. A good one, sure, but a business that goes up and down with game releases. Meanwhile, NVIDIA is pouring a fortune into R&D for this tiny little compute market. And the worst part? All that spending was making their main product, their gaming chips, more expensive and power-hungry for features that gamers didn't even care about. It just didn't make sense to anyone on the outside.
And get this. This wasn't happening in some calm, stable market. Oh no, this was right as the world was basically on fire. The 2008 financial crisis hits. Then, on top of that, NVIDIA has its own major technical problems. The stock price just gets hammered, year after year. Investors weren't just skeptical. They were openly hostile. They were calling this whole CUDA thing a massive, costly distraction.
And we're talking about real, tangible pressure. In 2008, a bunch of their chips failed because of a packaging defect. The cost? A cool $200 million. Just gone. You can imagine how that went over with Wall Street. It just poured gasoline on the fire. But here's the crazy part. Inside NVIDIA, the belief was rock solid. While the entire world is screaming at them to get back to their lane, just make gaming chips, the CEO, Jensen Huang, is basically telling anyone who will listen that accelerated computing isn't just an idea, it's the inevitable future. That's the real tension here, right? This massive disconnect between the outside world and their internal conviction.
So the big question is, with all that heat, how on earth did they not fold? Well, this is where the story takes a turn, because NVIDIA's salvation came from three, let's call them unlikely lifelines. Three completely separate niche industries that started quietly tinkering with CUDA. And that quiet tinkering, it was everything.
All right, lifeline number one, scientists. Specifically, a field called molecular dynamics. Picture this. Researchers trying to simulate the unbelievably complex dance of every single atom inside a protein. It's a problem with a gazillion tiny calculations that all need to happen at once. And you know what's perfect for that? A GPU. And when these researchers, folks at places like the University of Illinois, finally got their code running on CUDA, the results were just insane. We're not talking about a little speed bump. This was a total transformation. It was the proof, the honest-to-goodness proof, that this whole idea wasn't just a fantasy.
I mean, how insane! Up to 100 times faster. 100x! That was the moment they proved that GPUs weren't just toys for playing games. They could do real, hard science, and do it at speeds that nobody even thought was possible.
Okay, so scientists were on board, but lifeline number two was where the real money came in, the oil and gas industry. These companies use this super complex technique called reverse time migration. Basically, it's a way to create these incredibly detailed 3D maps of what's buried deep underground. As you can guess, it's insanely math-heavy. Now, on the old CPUs, crunching the data for just one of these surveys could take months. Months! But when companies like Chevron and Hess tried it on NVIDIA's GPUs, that timeline just completely collapsed. We're talking a 15 times speed up. Something that used to take months could now be done in a matter of weeks. In an industry where a single day can be worth millions of dollars, that wasn't just an improvement. It was a total game changer. And here's the key part. The money they made from these big oil deals, it was high margin and it basically funded the entire future of their data center business. And last but not least, lifeline number three, Wall Street. You've got these huge financial firms running what are called Monte Carlo simulations to figure out the price of really complex derivatives. In their world, a millisecond isn't just a unit of time, it's the difference between making millions and losing millions. So here was NVIDIA's killer sales pitch to them. See all those racks and racks of servers you have? A handful of our GPUs can do the same job. It wasn't just about being faster, it was about being way more efficient, shrinking your data center and slashing your electricity and cooling bills. That idea, server consolidation, that became their very first real pitch to big business. So okay, they've got these three lifelines keeping them afloat: science, oil, and finance. But just surviving was never the plan. NVIDIA used that breathing room to start playing the long game, to build an entire ecosystem around their tech. That cash coming in from oil and finance, it wasn't just profit to put in the bank, it was fuel, and they poured every drop of it back into the company. Not just to build better hardware, but to build something bigger, an army of developers. And their strategy was just brilliant and super methodical. Step one, they started funding university research, creating these CUDA centers of excellence. Step two, they just gave away hardware and grants to get their tech into the hands of the smartest students.
Step 3, and this is a masterstroke, they helped write the textbook on parallel programming. The goal was simple, but so smart. Train an entire generation of programmers to think in CUDA before they even graduated. And so, all of it, that stubborn, crazy conviction, those weird, unlikely allies, that brilliant plan to seed the universities, it all came together. It built the foundation. So that when the AI revolution finally exploded around 2012, NVIDIA wasn't just ready for it. They were basically the only game in town. They had the tools, they had the ecosystem, and they had that army of developers ready to go. And really, that's the whole story in a nutshell, isn't it? On the outside, what did the world see? A struggling gaming company with a weird, expensive hobby. But what was actually happening underneath? They were building the engine that would power the next 50 years of computing.
Okay, so to really get how big of a deal this was, you have to understand what the world of AI looked like before 2012. And honestly, it was kind of stuck. For decades, progress had just crawled along. Researchers even have a name for it, the AI winter. It's when the funding basically vanished and big breakthroughs just felt like they were never going to happen.
And here's the wild part. The main idea behind all this modern AI, the neural network, it's not new at all. I mean, it was invented way back in the 1950s. So what was the problem? Well, it was an idea that was just way ahead of its time. For it to work, you needed two things that just didn't exist back then: an absolutely enormous amount of data and just an insane amount of processing power.
And because of those limitations, the whole idea was basically just shelved. And this wasn't just a few people thinking this way. No, the prevailing wisdom, the consensus among all the top AI researchers, was that neural nets were a total dead end, a failed experiment. Over.
Yeah, I mean, the smartest people in the field had completely moved on. They were pouring all their time and energy into other things, like this really complex method called support vector machines. That was supposed to be the future of AI. The key thing to remember here is that nobody, literally nobody, was looking at neural networks and thinking, hey, that's where the next big breakthrough is coming from.
And that's when this small, little-known team from the University of Toronto decided, you know what, let's take a gamble on this old, forgotten tech. And they decided to power it with a tool that back then, nobody in serious AI research was even looking at.
The whole thing went down at the 2012 ImageNet Challenge, which is basically the Olympics for computer vision. The goal? Simple. Build an AI that can recognize what's in a picture. So you've got this team, Alex Krzyzewski, Ilya Sutskever, and the legendary Geoffrey Hinton. They built this massive, really ambitious neural network they called AlexNet. But they ran smack into a huge problem. The normal computer processors, CPUs, were just way too slow to train their model. It would have taken forever.
So what was their solution? Was it some multi-million-dollar government supercomputer? Nope. It was something you could literally just go out and buy at a computer store. Two NVIDIA GeForce GTX 580s, plain old consumer gaming cards. Now this was an incredibly smart, practical choice. They were cheap, and more importantly, you could program them using NVIDIA's software called CUDA.
But even that wasn't straightforward. See, their AI model was so big it couldn't even fit on one card's tiny 3 gigabytes of memory. So Krzyzewski did something absolutely brilliant. He wrote special, custom code that literally split the model in half. He forced the two GPUs to talk to each other, sharing the massive workload. This trick, which we now call model parallelism, was a huge breakthrough all on its own.
All right, so the date is September 30th, 2012. The results of the competition are about to be released, and with them, the entire field of AI research was about to be completely flipped on its head.
So you gotta wonder, right? After all that, using this dead-end technology powered by a couple of gaming cards they hacked together, how did they actually do? How did they stack up against the best AI teams in the world?
Well, they didn't just win, they absolutely demolished the competition. Just look at this chart. It shows the error rate, and lower is better. AlexNet came in with a 15.3% error rate. The runner-up, using all the traditional state-of-the-art methods, they were stuck way up at 26.2%. I mean, that's not just a step forward, that's a whole new staircase. The gap was just unbelievable.
The result was so definitive, so shocking, that it basically ended the decades-long argument right then and there, overnight. Neural networks weren't a dead end after all. They were the future, and in a single day, pretty much everyone in the field knew it. And the change was instant. I mean, by the very next year's ImageNet competition, the entire field looked different. Those old methods were basically thrown out.
Almost every single top team was now using the exact same approach that AlexNet had pioneered: neural networks running on gaming GPUs.
Okay, so this huge academic earthquake sent massive shockwaves into the business world. And in one particular company, a CEO had this incredible aha moment.
You see, while most of the other big tech giants were looking at this and thinking, that's a neat little software curiosity, NVIDIA's CEO Jensen Huang saw something completely different. He instantly recognized that this AI training was the killer app that his GPUs had been waiting for. He knew right away that these researchers were about to become his most important customers.
And NVIDIA didn't just sit on this idea, they went all in. They immediately started tweaking their software to get better at the specific math that neural networks use. They built entire libraries, like CUDA and N, just to make deep learning faster and easier for researchers. They even changed the physical design of their upcoming chips, prioritizing AI calculations over purely gaming stuff.
But this pivot wasn't just about changing some product plans on a whiteboard. It meant changing the entire culture of the company from the inside out.
Think about it. All of a sudden, their sales guys weren't just talking to gamers who wanted to play the latest titles. They were talking to data scientists who had a totally different set of needs. These new customers couldn't care less about cool graphics. They cared about raw data throughput for training runs that could take weeks. It was a massive learning curve for the whole company.
And this really changed how NVIDIA even defines success. For years, the company was obsessed with one metric: frames per second, for making games look smooth. Now, their new obsession became floating point operations per second, just the raw mathematical muscle that AI needs. That simple switch in what they measured really tells the whole story of a company completely reinventing itself.
Okay, so this is where it all starts. Around 2015, they made this huge, deliberate, and frankly, really risky shift. See, everyone else was still making these general-purpose chips, but NVIDIA, they went all in. They started building what you could only describe as a new kind of hardware, a weapon, really, forged specifically for the AI wars they saw coming on the horizon. And they didn't waste any time. The pace was just unbelievable. In 2016, boom, they dropped the Pascal P100. And this thing, it wasn't just another graphics card. It was a targeted weapon for AI. But they didn't stop there. Just 1 year later, 1 year, the Volta V100 comes out and just completely rewrites the rules.
And that right there is the key. You have to understand, the P100 wasn't some souped-up gaming GPU that just happened to be good at AI stuff. No way. This was built from scratch, from the ground up, with one primary mission: deep learning. It was a massive statement of intent, and it came packed with some brand new critical tech. So what was this new tech? It was called NVLink, and here's why it was such a game changer. AI models were getting huge, like ridiculously big. A single GPU couldn't handle them anymore. NVLink was basically a superhighway that let a bunch of GPUs talk to each other directly, bypassing all the slow stuff in the computer. It let them act like one single massive GPU. And for training the kind of AI we have today, that wasn't just nice to have, it was absolutely essential. But okay, that was just the start. The hardware evolution was just getting warmed up. A year later, they did something that totally separated them from the pack. They literally started designing silicon to do a brand new kind of math, bending Moore's law to their will. Yeah, the Volta V100, that was the definitive moment. That was the fork in the road. This is where NVIDIA's AI chips and their gaming chips, which had been cousins for a while, went their separate ways, down totally different evolutionary paths. And the whole reason for this split? It was a tiny but incredibly powerful piece of specialized silicon. They called it the Tensor core, and here's the best way to think about it. Imagine a Swiss Army knife. It can do a lot of things, just okay. That's a regular chip. A Tensor core, though, that's like a master surgeon's scalpel. It's designed to do one single thing, and it does that one thing with absolutely mind-blowing speed and precision. So what's this one special job it does? Well, it's this specific calculation right here. Now, I know it looks like something straight out of a high school algebra class, but this one operation, this is the fundamental mathematical heartbeat of all deep learning. It's the building block. And to train just one AI model, you have to do this calculation billions and billions and billions of times. And the result of specializing like this, it was just staggering. I mean, look at this. You had your traditional CPUs just kind of chugging along, sticking to Moore's law, maybe doubling in performance every couple of years. But NVIDIA, with these new Tensor cores, they got a 10x performance leap for AI workloads. They weren't just playing the same game anymore. They had completely changed the rules. So this insane hardware speed basically created a vacuum that no one else could even come close to filling. But here's the twist in the story. The hardware, that was only half of it. The second, and you could argue even more important pillar of their empire, was the software. It's not just about the silicon. Check this out. By 2018, their software platform, which is called CUDA, had millions of developers. Just let that number sink in. Millions. The best way to think of CUDA is like the operating system for their GPUs. And this wasn't just a bunch of people using their product. It was an entire army of the world's smartest developers and researchers who all spoke one language, NVIDIA's. And this is where the moat gets really deep. Think about the major AI frameworks, right? TensorFlow from Google, PyTorch from Meta, Caffe. All of them, every single one, was built on top of NVIDIA's CUDA. So you see, NVIDIA wasn't just in the AI ecosystem. For all practical purposes, they were the ecosystem. So what did that mean for an actual developer sitting at their keyboard? It meant everything was just easy. You wanted to use the latest and greatest AI framework? You type in a simple command like pip install TensorFlow, and on an NVIDIA card, it just worked, instantly. That simplicity, that was a killer feature. Because let's talk about the alternative for a second. If you tried to get these same tools running on a competitor's hardware, oh, it was a total nightmare. The software was buggy, it was slow, you'd spend days just trying to get things configured. And in the world of AI research where speed is everything, that's just a complete non-starter, a death sentence. So when you combine that massive built-in community of developers with this simple, it just works experience, well, you get a software moat, a virtually insurmountable one. It became this incredible defensive wall around their entire business. Okay, so we've got the hardware, we've got the unbeatable software moat, but that brings us to the final piece of the puzzle. And honestly, this might be the most brilliant part of their whole strategy. It wasn't enough to win the market today. They wanted to lock in the future by capturing the mind share of an entire generation. See, for years, NVIDIA had been supporting universities and research labs, and now that investment was paying off in a huge way. A whole generation of PhDs, the smartest minds in AI, were graduating from the top schools in the world, and they had spent the last 5, 6, 7 years of their lives thinking, dreaming, and building exclusively in one single ecosystem, CUDA. It wasn't just a tool for them, it was their native language. And this is what makes it so hard for anyone else to compete. The cost of switching away from NVIDIA, it's not really about the price of the hardware. That's the small part. The real astronomical cost is the intellectual capital. It's the cost of retraining your entire team of brilliant, expensive researchers who only know how to think in CUDA. You'd have to retrain an entire community. It's almost unthinkable. Okay, so to really understand where NVIDIA is today, you have to stop thinking of them as just a chip company. They're way more than that. They're like the foundational layer for pretty much all modern AI development. This quote here, man, it just nails it. The engine room. That's exactly what they are. Seriously, without their hardware, the large language models, all the generative AI tools we're seeing pop up everywhere, they just wouldn't exist. Not at this scale. No way. So how did they become the engine room? Well, it really comes down to a few key pieces of hardware. Back in 2020, their A100 chip was a huge deal, but it was the H100, which came out in 2022, that just changed the game completely. During the AI boom, this single chip became like the new gold in Silicon Valley. It was the most sought-after thing in the entire tech world, period. But what was so special about these chips? Why couldn't other companies just copy them and build something similar? Well, the secret is quite literally baked right into the silicon. This right here is their secret weapon, transformer engines. And that's not just some cool marketing name. What NVIDIA did was physically build specialized logic. We're talking actual dedicated pathways in the chip, designed to do one thing and one thing only: accelerate the transformer architecture. And yeah, that's the T in GPT. So instead of making a chip that was pretty good at a bunch of things, they forged a highly specialized weapon for AI. And this is what gave them such an insane speed advantage. Think about it this way. While all their competitors were playing it safe, kind of waiting around to see which AI model would become the industry standard, NVIDIA was reading the early research papers. They saw this transformer bullet train coming and just started laying the tracks for it immediately. That deep connection to the research community put them light years ahead of everybody else. But look, having a revolutionary chip, even one this good, is only half the story.
The true genius of NVIDIA was seeing the much bigger picture. They weren't just trying to build a faster engine, they were designing the entire factory. This is the huge shift in how they do business. They figured out that companies don't just want to buy a box of GPUs and figure it out themselves. No, they want a fully functioning, high-performance system that's ready to go on day one. They want to buy the whole factory, not just the individual machines for the assembly line. And here's why that factory model is so brilliant. When you're trying to train one of these giant AI models, you need thousands of these GPUs all working together, right? But here's the problem. Having the fastest chips in the world doesn't mean a thing if they can't talk to each other fast enough. The network that connects them all, that becomes the real traffic jam, the real bottleneck. And NVIDIA saw this problem coming from a mile away. So in 2020, they made a move for a cool $7 billion that was just an absolute masterstroke. They bought a company called Mellanox. Mellanox made the fastest networking tech out there, stuff called Infiniband. By buying them, NVIDIA basically solved the bottleneck problem before most of their own customers even realized it was about to become their biggest headache. And this is how they built that whole factory. They now control every single critical piece of the puzzle, all the way up the stack. It starts with a tiny transistor on the GPU chip itself. Then there's the Mellanox network that ties them all together. Then the DGX servers that house everything. And maybe most important of all, the CUDA software that makes it all work. They're not selling you parts anymore. They're selling you a complete turnkey supercomputer. Now, if you just glance at their stock chart today, you'd think this was just a smooth, straight line to the top. But let me tell you, the reality has been way, way more volatile than that. You have to remember, the chip industry is famous for being cyclical. It has these massive, incredible booms followed by these really painful busts. And for a long, long time, NVIDIA was right there on that roller coaster with everyone else. This timeline really tells the story of that roller coaster. Back in 2018, you had the crypto hangover after the big mining boom, and the stock got hammered. Then they came roaring back with the A100, only to get hit again in 2022 with inventory issues after COVID. It was really the generative AI explosion that finally broke that cycle. It just unleashed this absolute tsunami of demand that the industry had never, ever seen before. So they've built this empire. The king is on the throne. But you know how it goes. As soon as you get to the top, the question immediately becomes, how do you defend it? What are the risks just over the horizon? First, let's just be clear about what they're defending. We are living through a fundamental re-platforming of all of information technology. For decades, the world ran on CPUs, which are great at following a list of instructions. Now, the world is shifting to GPUs, which are masters of, well, data and inference. This shift is a multi-trillion-dollar prize, and right now, NVIDIA has something pretty close to a monopoly on it. And with a prize that big, you can bet there are threats. They're coming from a couple of different directions. On the geopolitical side, you have governments putting export controls in place, especially to a massive market like China, and that could really limit their growth. And then you have the competition. Their own biggest customers, we're talking Google, Amazon, Microsoft, they are all racing to design their own custom AI chips to try and break free from relying so heavily on NVIDIA. But, and this is a huge but, NVIDIA has an ace up their sleeve. It's their ultimate trump card. It isn't just the hardware, it's the CUDA software platform. Millions of developers and AI researchers have spent more than a decade building everything on top of CUDA. To switch to a competitor's chip means you have to rewrite all of that code. That software moat is just incredibly wide, and it's going to be really, really tough for any competitor to cross. And really, this whole thing boils down to two totally different philosophies about how to get a job done, right? Do you hire one brilliant expert who does everything perfectly, one step at a time, or do you hire a massive army to do thousands of simple things all at the exact same time?
All right, first up, let's talk about the incumbent, the champ, the one that's been running the show in computing for decades, the CPU. And a great way to think about it is like a master craftsman. So the CPU, that's the central processing unit, it's basically the brain in your laptop, your phone, you name it. Its whole design is built for one thing: handling really complex jobs that have to happen in a very specific order. One thing after another after another.
And that master craftsman analogy, it's perfect. Or think of a head chef in a 5-star kitchen. It is just brilliant at juggling a ton of different complicated instructions that all depend on each other. That's what lets your operating system and all your apps run so smoothly.
So let's break down what that craftsmanship really means. A CPU is built for what we call low latency. That just means it's incredibly fast at finishing one single job. It's got all this complex logic and these big memory caches to guess what you're going to do next, which makes it the perfect all-rounder for just, everyday computer stuff. But then, a new kind of problem showed up. A problem that the CPU, with its brilliant jack-of-all-trades design, was just not built to handle. And that problem was the absolutely insane appetite for math that modern AI has. And here's the real mind-bender. Training a huge AI model isn't about making complicated decisions. Not at all. It's about something way, way simpler. Just raw, brute force math. But on a scale that is almost impossible to imagine. So what does this AI work actually look like? Well, we're talking quintillions. Yeah, quintillions of super simple, super repetitive calculations. It's just multiplying these giant grids of numbers, we call them matrices, again and again and again. And all that is just to tweak the billions, sometimes trillions of little knobs and dials that make up a model like GPT-4. And this is the absolute key. For this kind of job, the CPU's fancy design, all those complex parts and big caches, they actually become a liability. They just get in the way. They're taking up precious space and power that could be used for that simple math. It's like asking our master chef to spend all day just making toast. It's a massive waste of talent. And that exact inefficiency, it cracked the door wide open for a challenger, a real underdog, something that was never, ever designed for this kind of work. So, enter the GPU, our parallel army. Now, the GPU, the graphics processing unit, it had a totally different day job to start. Its whole purpose in life was to make your video games look amazing. I mean, it was built specifically to figure out the color and lighting for millions of pixels on your screen, all at the exact same instant. So its philosophy is the complete polar opposite of the CPU's. Instead of that one master craftsman, the GPU is this huge, sprawling army of simple workers. The goal isn't to do one complicated thing super fast. Nope, it's to do thousands of simple things all at once. Okay, so let's put these two side by side, a real head-to-head. Let's really see how this showdown between the craftsman and the army shakes out. And here's the difference in a nutshell. The CPU, it's got a handful of really powerful, complex cores. They're all about that low latency, right? Being super fast on one single thing. The GPU, on the other hand, has thousands of simple, efficient cores, and they are all about high throughput, which is just a fancy way of saying they get a truly massive amount of total work done all at once. Just to give you a sense of scale here, a really, really high-end CPU, a beast of a chip, might have what? 64 cores? So that's like having 64 master craftsmen in your workshop. Okay, now compare that to a modern GPU built for AI. We're talking tens of thousands of cores. It's not even in the same league. It's not a fair fight. It's a tiny workshop going up against a factory the size of a city. So, how did this all end? Well, that staggering difference in the number of cores, that's the reason the GPU's parallel army just completely ran away with the AI race. It's actually pretty clever how it works. You take a giant AI math problem and you chop it up into thousands of little identical pieces. Then you hand one tiny piece to each one of those thousands of cores. They all do their little bit of math simultaneously at the exact same moment. And then, poof, the results are all combined. The speed up you get from this is just, it's astronomical. So here's the big takeaway, the thing to really remember. The GPU makes a trade. It gives up being the fastest at any one single thing in exchange for a mind-blowing increase in the total amount of work it can do all at once. And that trade-off, swapping that single task speed for massive overall throughput, that is the absolute foundation of the entire AI world we see today. It was this sort of beautiful accident, right? The GPU's architecture just happened to be the perfect match for the kind of math that deep learning needs, and it totally transformed it. I mean, it went from being this thing for gamers into the literal engine powering the biggest tech revolution of our lifetime. We are digging into the story behind NVIDIA's complete and utter dominance in AI hardware. You see, it's a story of just relentless innovation, where every new chip they release doesn't just get a little faster, No, it fundamentally rewrites the roles of what's even possible with artificial intelligence. Okay, so to really get this, you have to understand the core idea that drives everything. It's what we call a virtuous cycle. Think of it like this. NVIDIA builds better, way more powerful hardware. This new hardware then lets researchers build these huge, much more capable AI models. And guess what? Those massive new models create a totally insatiable hunger for even more powerful hardware. It's this feedback loop that's just been spinning faster and faster for years. And the engine powering this whole cycle? It's NVIDIA's absolutely relentless pace of innovation. You can actually trace this silicon family tree through 3 really groundbreaking architectures that have pretty much defined the modern age of AI. So let's look at how this whole thing unfolds. It all kicks off back in 2020 with the Ampere architecture. That was the foundation. Then in 2022, Hopper came along and just slammed on the accelerator. And that brings us to today, 2024, and this massive, massive leap to Blackwell, which is, well, a total barrier breaker. All right, first up, Ampere. Dropping in 2020, this is the architecture that really, truly laid the groundwork for the whole generative AI boom that we're all living in right now. I mean, it was the perfect chip at the perfect time. Now, just to wrap your head around the insane scale of the A100's rollout, get this. It was the go-to workhorse behind huge models like OpenAI's GPT-4. Training that thing took a coordinated army of something like 20 to 25,000 of these A100 GPUs, all humming away for months straight. Just incredible. So what was the secret sauce inside Ampere? It was something called the 3rd generation Tensor core. The best way to think about these is like tiny, specialized brains living right on the chip. They're not for playing games or browsing the web. Nope. They are built for one single purpose: to perform the exact kind of matrix math that is the beating heart of all modern AI, and to do it unbelievably fast. And this is where it gets really clever. Ampere had this brilliant solution to a huge problem. See, AI researchers needed the rock-solid stability of high-precision math, but they also craved the raw speed of low precision. So what did NVIDIA do? They created TF32. It just took the best of both worlds. It had the huge dynamic range of FP32, but the speed of a faster format. And you know the best part? It all happened automatically. Developers didn't have to change a single line of their code. So if Ampere built the foundation, the Hopper architecture, which came out in 2022, was like pouring gasoline on the fire. It was custom built for this new wave of AI models that were just starting to take over the world. Right, so here's the crucial point. The H100 GPU wasn't just a slightly faster A100. Oh no, it was explicitly, from the ground up, engineered for the transformer architecture. You know, the T in GPT? That's the design that powers basically every single modern large language model you've heard of, from ChatGPT to Gemini and beyond. Hopper's signature move is something called the transformer engine. It's this amazing blend of hardware and software that does something pretty remarkable. It actually watches the data as it flows through the chip and decides on the fly when it can switch down to an even faster, lower precision format called FP8 without messing up the model's final accuracy. It's just so smart. In this dynamic precision thing, it led to a performance jump that was absolutely staggering. I mean, for just general AI training, the H100 was way faster than the A100. But for inference, actually using a big language model to get an answer, it was up to 30 times faster. 30! That is a colossal generational leap. Okay, but by 2024, even with all that incredible power, NVIDIA was slamming into a really fundamental problem. And it wasn't a software problem. It was a physical one. A wall. And getting past it was going to require a completely radical, new way of thinking about how you even build a chip. That wall has a name. It's called the reticle limit. Basically, it's the maximum physical size of a single slice of silicon that our current technology can manufacture. You literally could not print a bigger, more powerful single chip, even if you wanted to. They had hit a hard ceiling imposed by the laws of physics. So, if you can't make one giant chip, what on earth do you do? Well, NVIDIA's answer was genius. They decided to fuse 2 absolutely massive chips together. They're connected by this ridiculously fast interconnect so that to the software, they look and act like one single gargantuan GPU. And this whole chiplet design let them just completely smash through the old limits. They managed to pack an almost unbelievable 208 billion transistors onto the B200 GPU. To put that in perspective, that's more than 2.5 times the number of transistors on the already huge H100. Blackwell also just keeps pushing the boundaries of precision. It introduces a new 4-bit format called FP4, which can in theory double performance again. Now, using only 4 bits of data is super risky. You could lose a ton of accuracy. So they had to invent new hardware tricks like micro-tensor scaling just to keep all the math stable. So what's the end result of all this wild innovation? Yet another mind-boggling jump in performance. When you're talking about training the next generation of absolutely giant trillion-parameter AI models, Blackwell promises up to a 30-fold speed up compared to even the mighty Hopper. And this next part might be just as important, if not more so. It's also 25 times more energy efficient. Now, this isn't just some nice little side benefit. This is absolutely critical for making sure the future of AI is actually sustainable. So, okay, we've just walked through this whole silicon family tree. But what does this relentless march forward from Ampere to Hopper to Blackwell, what does it actually mean for the future of AI? Why should you care? This really sums up the whole journey perfectly. Each generation looked at the biggest problem holding AI back and just solved it. Ampere solved that battle between precision and speed. Hopper cracked the code on scaling up transformer models. And Blackwell? Well, Blackwell solves the problem of physics itself. Each step just pours more fuel on that virtuous cycle. And that's exactly why those huge efficiency gains are so important. This isn't just about making AI faster for the sake of speed. It's about making the future of AI even possible. Without these kinds of breakthroughs, the amount of power needed to run the next wave of models would just be so enormous it would become totally unsustainable, both economically and for the planet. So everyone is talking about NVIDIA's GPUs, right? They're the brains powering this whole AI explosion. But today, we're going to pull back the curtain on their real secret weapon, the unsung hero that actually makes it all possible, the network. Let's dive in. Now, this sounds like a totally crazy question. I mean, how can a $40,000 tip, the most powerful of its kind, be completely useless by itself? Well, the answer to that question gets right to the heart of how these massive AI models are built, and it explains why NVIDIA's dominance is about so much more than just a piece of silicon. And this quote right here, this is the key. The whole game has changed. We're not thinking about the power of one computer chip anymore. We're thinking about the power of an entire building, a whole data center working as one giant machine. The data center is the computer. Okay, so here's our game plan. First, we'll tackle the insane scale of the AI problem. Then we'll look at the massive communication bottleneck that creates. After that, we'll go deep inside NVIDIA's AI supercomputers and then zoom out to see how they connect thousands of them. And finally, we'll see how all of this builds an almost unbeatable business advantage. So let's kick things off with the scaling problem. We've gone from needing a single powerful chip to needing what's basically a city of computers, all focused on solving a single problem. The thing is, one GPU, no matter how ridiculously fast it is, just can't handle training a model like GPT-4. It's not even close. It's a team sport, and we're talking a massive team. Tens of thousands of GPUs all needing to communicate and work together in perfect harmony, almost like they share one mind. And all that teamwork, all that communication, well, it creates the biggest headache in modern computing, a gigantic high-speed traffic jam. So the question becomes, how do you get all of these GPUs talking without bringing the whole system to a screeching halt? Now, you might be thinking, don't data centers already have super fast networks? And they do, but they're built for a totally different kind of traffic. Traditional web traffic is bursty, like a bunch of separate phone calls. AI training, though, is an all-to-all constant conversation. Every single GPU needs to talk to every other GPU all the time. Standard networks just choke on that. And if a GPU is just sitting there waiting for data, that's literally millions of dollars of hardware doing absolutely nothing. So what are they all so busy talking about? They're sharing these things called gradients. You can think of a gradient as a tiny little progress report. Each GPU works on a small piece of the puzzle and then needs to share what it learned with everyone else. If those little reports get stuck in traffic, the entire learning process just grinds to a halt. So how did NVIDIA solve this traffic nightmare? Well, let's zoom in and look at how they connect GPUs inside just one server, turning dozens of chips into what feels like a single massive brain. Their foundational piece of magic is called NVLink. The best way to think about it is as a private 8-lane superhighway built only for GPUs. It completely avoids the normal computer connections, which are more like slow, congested city streets in comparison. And the speed on the superhighway is just staggering. We're talking 900 gigabits per second of bandwidth for every single GPU. That's an absolutely colossal amount of data, and it lets all those GPUs share their progress reports almost instantly. Okay, so NVLink is great for connecting a handful of GPUs. But how do you scale it up? Well, that's where the NV switch comes in. It's a special chip that acts like a massive intelligent traffic interchange, weaving all those private superhighways together into a seamless, bigger network. And when you put it all together, you get something like this, the GB200 NV72. This is an entire server rack, sold as one unit, packed with 72 of their latest Blackwell GPUs, all interconnected with the huge spine of those NV switches. And here's the punchline. The total communication speed between any two GPUs in that rack is 1.8 times terabits per second. This is what lets all 72 of them act as one single unified processor. It's a monster. So that's how you solve the traffic problem inside one box. But to train the biggest models, you need thousands of these boxes. How do you connect all of them? This is a whole other level of challenge. And this is where traditional Ethernet, the stuff that runs the internet, just hits a wall. See, the internet was designed to be lossy. If a packet of data from a website gets lost, your computer just asks for it again. No big deal. But in AI training, a single dropped packet is a disaster. It can throw off the calculations for the entire system. You need a lossless network, period. And just look at the difference that makes in the real world. Under heavy AI workloads, a standard Ethernet network is lucky to be about 60% efficient. But NVIDIA's Spectrum X platform, it's hitting 95% efficiency. That's not just a little better, it's a monumental leap in performance. So how does it pull this off? Well, Spectrum X is just plain smarter. It's like having ways for your data packets. It uses incredibly sophisticated routing and congestion control to see traffic jams before they happen and intelligently reroutes data to avoid them. The result is specialized, lossless performance, but on standard off-the-shelf cables. All right, let's tie all of this tech back to the business, because this complete networking stack is what gives NVIDIA its deep, powerful competitive advantage, what investors would call its moat. So here's the whole picture. It's a 3-layer solution. At the very bottom, you have NVLink connecting GPUs. Then you have NVSwitch unifying an entire rack. And on top of it all, you have Spectrum X connecting the entire data center. It's a complete, end-to-end, fully integrated system that they control. And this is the most important takeaway. NVIDIA isn't just selling you computer chips anymore. They're not just selling you the tools to build something. They are selling the entire pre-built, fine-tuned AI factory. The networking is every bit as important as the silicon. And by owning the whole stack, they deliver performance that's incredibly difficult for anyone else to match. We're going to figure out why NVIDIA has this seemingly unbreakable grip on the entire world of AI. And really, it all boils down to this one question, right? With so much money, so much on the line, why can't anybody seem to catch NVIDIA in this AI race? Well, the answer, it's not just about the chips. It's all about the software. Okay, so let's get right into it. To really get a handle on NVIDIA's dominance, you've got to imagine a fortress, a massive one. And the moat protecting this thing, it's not filled with water, it's filled with almost 20 years of pure code. Right at the heart of that fortress, you'll find one thing, CUDA. Put simply, CUDA is the magic key. It's the software that lets developers take all that raw parallel processing power from NVIDIA's GPUs, the ones originally built for making games look pretty, and use it for these incredibly complex jobs, like, AI. But here's the thing, it's not just one program, not even close. It's an entire ecosystem that they've been building for nearly 2 decades. I want you to think of it like a giant specialized library, just packed with all this pre-written, super optimized code. We're talking about tools like cuDNN and QBLAS that are just perfectly tuned for NVIDIA's own hardware. It gives developers a huge head start. And this is where the uphill battle for everyone else becomes painfully clear. You see, for competitors like AMD or Intel,
the problem isn't just about making a faster chip. No way. They have to build an entire software stack from the ground up that can run all the AI code that's already out there flawlessly. Meanwhile, NVIDIA's just sitting there with this incredible advantage, a totally mature ecosystem that developers already know, they already trust, and frankly, they've built their entire careers on. But, the fight is always shifting. The ground is moving. And now we're entering a brand new battlefield. It's all about something called AI inference. So what's so important about this? Well, for years, the really hard part was training these massive AI models. But now, the focus is all on inference. That's the actual running of the model, when you ask it a question or tell it to generate a picture. And in this new arena, efficiency is literally everything. I mean, every single bit of wasted computing power means higher costs. And that translates directly to slower chatbot responses or more expensive AI services for you and me. Okay, so if we're going to get a little technical for a second, the big challenge at the heart of inference is managing something called the KV cache. The easiest way to think about it is like this. It's the AI's short-term memory. It's the reason a chatbot can actually remember what you just said a second ago in your conversation. And here's the problem with that. The old way of handling this short-term memory was just incredibly rigid. It would basically block off one giant single chunk of memory for every single conversation. But think about it. Conversations are totally unpredictable. This old method led to massive amounts of wasted, fragmented space on these super expensive GPUs. It's like having a huge parking lot and only letting one car park in the middle, leaving all this valuable real estate just sitting there, completely empty. So this obvious inefficiency, it created a huge opening. And the open source community, they saw it, and they charged right through that gap with a really clever strategy. It's a library called VLLM. And its secret weapon is a technique called paged attention. So how in the world does this work? Well, it's actually a brilliant idea they borrowed from old-school computer operating systems. First, instead of that one big clunky block of memory, the KV cache, that short-term memory, gets broken up into these little flexible chunks called pages. Then a smart traffic cop, a manager, keeps track of all these pages and just slots them in wherever there's free space. The result? Boom. All that wasted, fragmented memory is pretty much gone. And the payoff for doing this is, well, it's incredible. It unlocks this technique called continuous batching. Basically, the GPU can now dynamically juggle a whole bunch of different user conversations all at the same time. The real-world impact here is just stunning. A single server can suddenly handle double or sometimes even triple the number of users it could before. That's a huge deal. Okay, so you just know NVIDIA wasn't going to sit back and let the open source world just walk away with a performance crown, right? Of course not. This led to the empire striking back with their own counterattack, a tool called Tensor RT-LLM. And NVIDIA's strategy here was really smart. They looked at what the open source folks did and said, yep, that flexible memory idea is a winner. So they adopted it. They called their version in-flight batching. But then they layered on their own secret sauce. These deep, proprietary optimizations that literally only they can do because they know their own hardware down to the very last transistor. And this is how they pull ahead. Tensor RT-LLM does some really clever stuff, like fusing a model's layers together to cut down on how much data has to move around. It uses these really deep optimizations for new, hyper-efficient ways of handling numbers, things like FP8 and FP4. And at the end of the day, it basically compiles the entire model into one single, perfectly streamlined program built just for their chips. So this all brings us to the core trade-off, the choice that developers have to make. What we see again and again in the benchmarks is that VLM, the open source tool, it often wins when it comes to flexibility and latency, how fast you can get a single answer back. But if you need to handle massive workloads, huge batches of requests, and squeeze every last drop of performance out of your hardware, well, that's when NVIDIA's proprietary Tensor RT-LLM usually takes the crown. But while this whole battle over inference performance is raging, there's another threat. Maybe an even bigger one that's quietly developing in the background. And this is what I'm calling the Triton twist. And this brings us full circle, all the way back to that fundamental problem for every single one of NVIDIA's competitors. Is there any way at all, to finally break that CUDA lock-in? Is it possible to tear down the walls of that software fortress for good? Well, the most promising answer we've seen so far might be a project from OpenAI called Triton.
Think of it like a universal translator for GPUs. It's an open-source language that lets a developer write high-performance code just once, and they don't have to be a super genius CUDA expert to do it.
And the goal here, this is truly a game changer. If Triton actually succeeds, the code written in it could, at least in theory, run just as efficiently on an AMD chip or an Intel chip as it does on an NVIDIA one. That would create true hardware independence. It would basically blow the gates of that fortress wide open. But, and you knew there was a but, here's the twist. The reality, at least for right now, is that Triton's backend, the part that actually does the translating to the hardware, is most optimized for, you guessed it, NVIDIA GPUs. So in this kind of profound irony, the very tool that was designed to break the lock-in is, for now, actually making it stronger.
We are living through an AI boom, and it's happening at a scale that's almost impossible to wrap your head around. We see all the incredible software, we hear about these mind-blowing new models, but underneath all of that, there's a hidden story. It's a story about physical limits, about manufacturing, about supply chains, and about the very real challenges of actually building this digital future. So you gotta ask, what's the real thing holding this revolution back? What's the one bottleneck that could slow down the true potential of AI? For years, we all thought the race was about designing faster, more powerful silicon. But it turns out the real bottleneck, the defining challenge of this entire AI boom, it's been something else entirely. It's about how you package those chips once you've made them. And that brings us to a super critical and really complex manufacturing process called CoWoS. This right here is the secret sauce behind the most powerful AI chips in the world, like NVIDIA's H100 and their new B200.
Okay, so what on earth is CoWoS? Well, the name's a mouthful. Chip on wafer on substrate. But the idea is pretty brilliant. It's an incredibly advanced way to get a powerful GPU and its super fast memory as close together as humanly possible. They're placed side by side on this special silicone base called an interposer, which basically slashes the distance data has to travel. And in the world of AI, that means more speed and way more efficiency.
Let's break it down. Think of it like building a tiny, hyper-connected city. First, you have to place your most important buildings, that's the GPU and the memory, onto a foundational grid, the interposer. Then you connect them with this insane network of microscopic superhighways called through-silicon vias, or TSVs. This lets data zip back and forth at unbelievable speeds. And finally, you package that whole city up so it can be plugged into the real world. Now the problem is, this is a very slow, high-precision process. And that's exactly what became the #1 bottleneck. Of course, that powerful GPU can't do its job all by itself. It needs instant access to just massive amounts of data. And for that, you need a very, very special kind of memory that works hand in glove with that CoWoS foundation. And the difference here is just night and day. A traditional gaming GPU uses something called GDDR memory. You can think of that like a sprawling suburb. All the chips are spread out. But AI GPUs, they use high bandwidth memory, or HBM. And this is like building a skyscraper. You're stacking memory chips vertically, one on top of the other, creating this incredibly dense and ridiculously fast connection right next to the GPU. That super short distance is the whole key to unlocking insane data bandwidth. And, the speed of innovation here is just staggering. NVIDIA's A100 chip used HBM2E. Then the H100, which really powered this whole generative AI explosion, it jumped to HBM3. And now, the new B200 is pushing things even further with HBM3E, which can shovel an incredible 8 terabytes of data per second to a single GPU. That's just wild. So who actually makes this critical stuff? Well, it's a very exclusive club. It's really dominated by 3 main players: SK Hynix, who's been the leader for a while, and then Samsung and Micron, right there with them. These are the companies building those memory skyscrapers. Okay, so you've got these 2 revolutionary components, CoWoS and HBM. And what happened in 2023 is that every single AI company on the planet suddenly wanted the exact same thing at the exact same time. Demand just blew past supply, and it created this global scramble. This number tells you everything you need to know about who has the power in this market. To make sure it wouldn't get left behind, NVIDIA reportedly went out and booked somewhere between 40 and 70% of TSMC's entire global CoWoS capacity for the next couple of years. That's an absolutely astonishing figure. It just shows you how critical this one single process has become. So the big question is, how does the industry even respond to a crisis like this?
The answer is simple. You build. You build like crazy. TSMC, which is the only company that can do this, started this massive expansion, basically aiming to more than double its CoWoS output in less than 2 years. It's a huge industrial mobilization. But this whole manufacturing race has exposed a much deeper, more strategic problem. It turns out it's not just about how much you can build, it's about where you build it. And here we get to the real heart of the issue, the elephant in the room. The entire cutting-edge supply chain for AI, from making the chips at TSMC to doing the advanced CoWoS packaging, it's all geographically concentrated in one place, Taiwan. And recognizing that geopolitical risk has kicked off a massive strategic shift. So what's the solution? It's all about redundancy. For the very first time, this incredibly complex process is being duplicated on American soil. TSMC is firing up its brand new fab in Arizona to make NVIDIA's latest wafers. And just as important, NVIDIA is partnering with companies like Amkor to replicate all those critical back-end steps, the packaging and testing, right here in the United States. When the very first of those next-gen wafers were produced in Arizona, it wasn't just some technical achievement. It was called a historic milestone. And that's because this represents a deliberate, strategic effort to bring the production of what are now considered vital national assets back home.
142%. You heard that right. That is the insane year-over-year growth for what is now NVIDIA's single most important business. And look, a number like that, it's more than just a good quarter. It's a signal of a massive, seismic shift, not just for NVIDIA, but for the whole tech industry. And honestly, it explains pretty much everything we're about to talk about.
So, for most of its life, if you said NVIDIA, people thought gaming, right? That was their whole deal. But just look at this breakdown for fiscal year 2025. The script has been completely flipped. Data center revenue, it's just exploded to over $115 billion. And gaming? It's sitting there at just over $11 billion. I mean, think about that. The part of the business that powers AI, which was basically a side gig not too long ago, now makes up almost 90% of their total revenue. It's just a total transformation.
Okay, so this just begs the question, right? What in the world happened? I mean, what kind of force is so powerful that it can completely rewrite the financial DNA of a massive, multi-billion-dollar company in just a handful of years? Well, the answer, as you've probably guessed, is the absolute explosion in AI.
We are right now in the middle of an AI gold rush. And like any gold rush, it's being driven by a massive spending spree, what the industry calls a CapEx cycle, or capital expenditure. You've got the world's biggest tech giants, the hyperscalers like Microsoft, Meta, Google, Amazon, and they are all locked in this insane arms race to build the smartest, most powerful AI. And to win, they are spending billions upon billions of dollars.
So, where is all that money going? Well, a huge chunk of it is going to NVIDIA. And this leads us to the hardware itself and what kind of looks like a paradox on the surface, because the chips these companies are buying are just incredibly, eye-wateringly expensive. So let's get into the core economics of what's actually powering this whole AI revolution.
Yeah, let's put a real number on this. Why on earth would a company pay up to $30,000 for a single chip, a single GPU? I mean, it sounds completely astronomical, right? But believe it or not, there's a very clear, very cold logic that actually makes it a really smart investment.
In that logic, it all comes down to a concept called total cost of ownership, or TCO. Think of it like buying a car. The sticker price is just the beginning, right? You also have to think about gas, insurance, maintenance. Well, it's the same here. The price of the chip is only one piece of the puzzle. To get the real cost, you have to look at the entire life of the system. And that includes huge, ongoing costs, like the electricity bill and even the real estate the servers are sitting on.
Okay, so here's how the whole TCO argument really works. Step 1, yes, you pay a ton of money up front. The sticker shock is real. But step 2 is the massive performance gain. These chips are just so much more powerful and, critically, so much more efficient. We're talking better performance for every watt of electricity and for every dollar you spend. And that leads to step 3, lower lifetime costs. Because they're so efficient, you need fewer servers, and this is the big one, way less electricity to get the same job done, and that just crushes those long-term operational costs.
Now, what's really smart is that this whole strategy feeds directly into their future. NVIDIA is not resting on its laurels here. They're not sitting still. The company is basically doubling down on this whole efficiency argument with their next generation of chips, which are codenamed Blackwell. This is their big bet to secure their dominance for years and years.
25 times. The new Blackwell platform is promising to be up to 25 times more energy efficient for running these huge AI models. I mean, just let that sink in for a second. Imagine slashing your energy costs by a factor of 25. For companies that are already spending billions, literally billions, on electricity, that's not just an improvement. That is a complete and total game changer.
And this, right here, leads directly to NVIDIA's killer sales pitch. It's so powerful, they can walk into a customer and say, look, by cutting your electricity bill and the number of servers you need this dramatically, upgrading to our new, more expensive hardware, well, it basically pays for itself. It stops being an expense and starts being a sound, economically rational decision.
So as AI starts to shift from just being trained in a lab to being used in our everyday lives, a phase called inference, there's a new metric that becomes super important: joules per token. It sounds complicated, but it's really simple. It's just a measure of how much energy it costs for an AI to do one tiny thing, like generate one word in a sentence. And by driving that cost down, 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 NVIDIA is making it cheap enough to stick AI into basically every app and service we use every single day.
Okay, so when you pull all of this together, the insane revenue flip, the brilliant logic of total cost of ownership, and this relentless focus on future efficiency, what you're really witnessing is a complete and fundamental shift in what this company even is.
What this all boils down to is this. NVIDIA has gone from being a company that sold you a component for your gaming PC to being, you could argue, the single most valuable infrastructure company in the world. They're not just selling parts anymore. They are selling the actual foundation, the plumbing, the electricity grid of the entire new AI economy.
Let's be real. When you think about AI, you probably picture code floating around in the cloud, right? Just pure data. But what if I told you the next huge leap in AI is actually being built with concrete, steel, and massive amounts of power? We're talking about the new AI gigafactories, these unbelievable industrial projects that are literally building the future of intelligence from the ground up. And this quote it hits the nail on the head. This abstract idea of computing power measured in flops, which, by the way, is just a nerdy way of saying how many calculations a computer can do per second, it's not theoretical anymore. It's not just a number on a spreadsheet. It is physically manifesting as steel, concrete, and some of the biggest construction sites on the planet. So, in this new world of AI gigafactories, you've got two titans leading the pack, xAI and Meta. Now, they're both racing towards the same goal: building the future of AI. But their game plans, they could not be more different. So let's dive in and look at their blueprints for this high-stakes race.
Okay, first up, we've got Elon Musk's xAI. Their big project is called Colossus, and it's being built out in Memphis, Tennessee. I mean, the name alone tells you they're not messing around. But their secret weapon, their real edge, isn't just about being big. It's about being fast, incredibly fast.
So what does Colossus actually look like? Well, picture this: 100,000 of NVIDIA's H100 GPUs all linked together. These things are the absolute engines of modern AI. And get this, that's just phase one. They're planning to double it. This one single project is just an insane concentration of raw compute power.
And here's where things get kind of mind-bending: the timeline. xAI got this entire monster of a facility up and running in just 122 days. To put that in perspective for you, a normal legacy data center, that takes anywhere from 1 to 2 years to build. What they did is just a blistering pace, and it means they can get their new models training way, way faster than their rivals. Of course, moving that fast and building that big, it's not cheap. Not even close. We're talking about billions of dollars, with a B, invested in just the hardware for this one cluster. It is a massive all-in bet on building one of the most powerful supercomputers in the world, and doing it faster than anyone has ever done it before.
So the billion-dollar question is, how on earth did they pull that off? Well, it boiled down to a few really clever choices. They used NVIDIA's prepackaged networking system and some super efficient liquid-cooled rocks from Supermicro. But, the real game changer was a little more boring. They just used standard Ethernet. By sticking with common parts, they completely simplified their supply chain and just built faster than anyone else.
So what's the point of all this power and speed? It's all being funneled into one thing: training the next generation of their models, called Grok 3. And because they're keeping it all proprietary, all in-house, they have total control. That speed lets them iterate and build new versions faster than anybody, and that's the core of their entire strategy. Okay, now let's completely switch gears and look at Meta.
This is a true study in contrast. They're also building at a ridiculous scale, but their whole philosophy, their big strategic bet, it's the polar opposite of XAI's. Meta has gone all in on open source AI. Now, don't get me wrong, they're still building a private fleet of hardware that's second to none. But here's the twist. Their goal is to use it to power public models like Llama that they give away for free. It's a fascinating play. Build the factory in secret so you can give the product away to the world. And when we talk about their commitment to scale, it is just staggering. To train their latest Llama 3 models, they used clusters of nearly 25,000 GPUs. That's a lot. But their goal by the end of this year? 600,000 H100 equivalents. The jump from where they are to where they're going is just enormous. So why build such a beast? What do you do with all that horsepower? Well, you feed it. You feed it an almost unimaginable amount of data, trillions of tokens. Think of tokens as the little pieces of words and ideas that AI learns from. Meta's strategy is to leverage the sheer scale to make their free open models so good that it just becomes the default, the industry standard that everyone else has to compete with. So there you have it. We've seen two totally different playbooks. On one side, you've got XAI with its lightning-fast, tightly integrated approach. And on the other, you've got Meta's massive, open-source-driven machine. Let's put them side by side and really see how these strategies stack up. All right, let's break down this strategic showdown. XAI is betting everything on speed and integration. Their key advantage is that insane 122-day deployment time, which lets them iterate super fast on their proprietary Grok 3 models. Now, Meta, they're betting on scale and openness. Their advantage is the ability to process these massive data sets to power their open-source Llama models, and they're doing it with a GPU target that's 6 times larger than what XAI is working with right now. So, what does this all add up to? Well, we're watching a new kind of arms race unfold in real time. But instead of missiles and tanks, the competition is over computing power. And the prize they're all fighting for isn't just a bigger market share or a slightly better app. Oh no, it's much, much bigger than that. And this, right here, is the key takeaway. The companies that win this gigafactory race, they aren't just building better software. By controlling the physical infrastructure that creates and trains artificial intelligence, they will have enormous power to shape how these systems evolve, who gets to use them, and ultimately what they can do. They are literally shaping the future of intelligence. There is a massive global conflict happening right now, but it's not being fought over oil fields or land. Nope. It's a war over these tiny, incredibly powerful pieces of silicon. We're talking about the hardware that powers artificial intelligence, and it has pretty much become the new oil, the most strategic resource of our time. And the ultimate prize in this whole conflict? It's something called sovereign AI. Just think about that for a second. It's the goal for so many nations right now to build and control their own AI infrastructure, their own data, their own talent. At the end of the day, it's all about technological freedom in a world that's going to be completely run by AI. So what is it that makes these little chips so unbelievably important? Well, it's because they are what's known as a dual-use technology. And that just means they're not only essential for building a booming economy, but they're also absolutely critical for creating next-generation military power. And what's just wild is that one company, NVIDIA, is sitting right at the heart of this huge geopolitical showdown. Their advanced GPUs, the chips that used to be famous for video games, are now seen as a strategic asset, so powerful they could literally shift the global balance of power. And that, right there, brings us to the core of this whole thing. The US government saw how critical these chips were becoming and decided it had to make a move. So it slapped on some really strict export controls to cut off China's access to these super powerful, top-of-the-line chips. And here's what that looks like in the real world. On the left, you've got NVIDIA's absolute best GPUs, the A100, the H100, the B200, total powerhouses, and now totally banned from being sold to China. So on the right, you have NVIDIA's clever little workaround, the H20 chip. It was specifically engineered to be just slow enough to get past those US export laws. So how on earth did NVIDIA manage to do that? Well, they made a really interesting trade-off. They intentionally slowed down or throttled the chip's raw computing power so it would be legal to export. But, and this is the key part, they kept the memory bandwidth really high.
That way, it's still pretty useful for what's called AI inference, which is basically just using an already trained AI model to make real-world decisions. Now, you can imagine, this whole maneuver came with a pretty hefty price tag for NVIDIA. The company had to take a $4.5 billion charge just for inventory adjustments related to these new chips. That's a staggering amount of money, and it really shows you just how disruptive these sanctions have been for everyone.
But here's the thing about moves like this. There's always an equal and opposite reaction. The US sanctions were designed to slow China's progress, right? Well, they had a major and maybe even unintended consequence. They basically created the perfect opportunity for a new domestic rival to jump in and fill that gap.
I mean, it's a textbook case of cause and effect. By blocking China from buying the best AI chips in the world, the US government essentially cleared the entire playing field over there. It created this protected space where a homegrown company could not just survive, but actually thrive.
And who was that competitor? Huawei. So now, Chinese companies had a choice. They could buy NVIDIA's slower, throttled H20 chip, or they could go with Huawei's Ascend 910B. And pretty quickly, it became a totally viable and, more importantly, a homegrown alternative. Just like that, you've got a brand new rivalry. And don't think for a second that this Ascend 910B is some cheap knockoff. No way. Huawei built its own really advanced interconnect tech, which lets them link thousands of these chips together into massive, powerful clusters. And on top of that, their software is getting better and better, making the whole package a really serious competitor. And believe me, Huawei is not planning on stopping there. Their ambition is crystal clear. Right now, their 910B chip is going head-to-head with NVIDIA's last generation. But by 2025, they're reportedly aiming for their next chip to compete directly with NVIDIA's super powerful H100. It just goes to show you, the sanctions might have bought some time, but they definitely didn't stop the race.
Okay, so this whole US-China rivalry didn't just stay between them. It sent massive shockwaves all around the world. It was a huge wake-up call for other countries, making them realize just how vulnerable they were and kicking off this frantic global race to build their own sovereign AI.
And the reason why is pretty simple, really. It's about survival. It's about independence. No country on Earth wants to get caught in the middle of this, having to rely completely on either American or Chinese tech for their own economic future and national security. The only logical answer is to build it yourself.
And we're already seeing this play out. Countries like Saudi Arabia and the United Arab Emirates are just pouring billions of dollars into building their own massive AI data centers using NVIDIA chips. Meanwhile, over in Europe, nations like France and the UK are also making huge investments to secure their own sovereign AI capabilities. But the US is still trying to be the gatekeeper in this game. So even when NVIDIA sells to allies, like in the Middle East, the US government now demands a special license for the sale. The whole point is to keep a tight leash on this technology and make absolutely sure that none of this top-tier hardware can be secretly rerouted or sold off to China.
Look, their latest Blackwell chip is an absolute monster, no doubt about it. But NVIDIA's always playing chess, thinking years ahead. So the real story isn't what they're doing right now. It's about what they're cooking up for 2026 and the huge fundamental problems they have to solve just to make it a reality.
NVIDIA's pace is just relentless. It's like clockwork. Every 2 years, boom, another massive leap forward. We had the A100 back in 2020, then the H100, and this year, of course, Blackwell. And now we actually know the next name on that roadmap, the one slated for 2026, Rubin. But you know what? Building this next one isn't going to be as straightforward as the last few. And that's because NVIDIA is basically smashing headfirst into the wall, a literal wall built by the laws of physics. To get to that next level, their Rubin chip has to solve two absolutely enormous problems. Problems that, if they're not solved, could honestly stop AI's progress dead in its tracks.
Okay, so problem number one is something called the memory wall. The best way to think about it is like this. Imagine your main processor is a world-class chef who can chop and cook at superhuman speed. But the ingredients, that's your data, are stuck in the world's worst traffic jam, trying to get from the pantry, which is the memory, to the kitchen. The chef is just standing there, tapping his foot, waiting. And what that creates is this massive widening gap in computing. Processing speed has just been skyrocketing, right? But memory speed, yeah, it's been lagging way, way behind. This gap, this is the single biggest bottleneck that's preventing us from building even bigger, more powerful, and smarter AI models. And the second problem? It's just raw brute force power. A single rack of the current Blackwell chips, not even the next-gen stuff, can pull down 120 kilowatts. That is enough to power dozens of homes. It's a truly staggering amount of energy. And where does all that energy go? It turns into heat. A lot of heat. And all of this leads to one single crucial conclusion. You just can't cool these things with fans anymore. It's not possible. For the most powerful AI systems, the old way of building data centers is officially a thing of the past. So, if you're NVIDIA, how do you even begin to solve these monumental problems? Well, their answer is the Rubin R100. And the solution isn't just about making it faster, it's about making it fundamentally smarter. Rubin basically attacks that memory wall with three big ideas. First, it uses this next-gen memory called HBM4 to build a much wider highway for the data to travel on. Second, it literally stacks a logic chip, like a tiny brain, right on top of the memory itself. And that enables the third and maybe the coolest breakthrough, near-memory processing. The memory can now do simple calculations all by itself, so the data doesn't always have to make that long commute to the main processor. This saves a ton of time and energy, which is just critical for training these massive models efficiently. And it's not just the main AI chip, by the way. The whole system gets an upgrade. Rubin is going to be paired with a brand new CPU called Vera. It's the successor to Grace, and it's specifically designed with cores that are optimized for one thing: feeding Rubin all the data it needs as fast and efficiently as possible. And that heat problem, remember that? Well, there's really only one answer. With Rubin, the power demands are so insane that liquid cooling isn't going to be an option anymore. It's going to be the mandatory, non-negotiable standard for any serious cutting-edge AI system, period. Okay, so Rubin is clearly the future. But that brings up a bigger question. How did NVIDIA get into this position where the entire tech industry just hangs on their every announcement? It's about so much more than just building fast chips. This quote right here, this really nails their whole strategy. They didn't just sell components. They sold a complete, integrated system. They took racks of what used to be individual computers and turned them into a single, cohesive AI factory where everything works together like one giant brain. This fortress they've built didn't just pop up overnight. It's the result of a strategy that's been going on for decades, and it goes way beyond engineering. It was deliberately built on three incredibly strong pillars that lock their customers in and keep their competitors out. First, you've got a unified hardware architecture that makes upgrading from one generation to the next totally seamless. Second, they have absolute mastery over an incredibly complex global supply chain. And third, this is the big one, is CUDA. That's their software. It's the language that lets developers actually use the hardware for AI. It's become the industry standard, and it's created this deep, powerful moat around their business that makes it unbelievably hard for anyone to switch to a competitor. But you know how these things go. No empire, no matter how dominant, lasts forever without a fight. And while NVIDIA is sitting comfortably on the throne right now, there are some very serious challengers gathering at the gates, and they're threatening the kingdom from all sides. So the battlefield for the future of AI is becoming really clear. On one side, you have NVIDIA's powerful, profitable, but tightly controlled closed ecosystem. And on the other side, you have this growing alliance of competitors and open source alternatives, all trying to tear those walls down. And the assault is coming on four main fronts. First, challengers are trying to exploit the very same physical limits that NVIDIA is battling. Second, geopolitical tensions are fracturing the global supply chain they rely on. Third, you have incredibly determined competitors pouring billions into R&D to try and catch up. And finally, you have these open software standards that are slowly but surely starting to chip away at CUDA's iron grip. For now, though, this quote really says it all. The challenges are very real, but the present reality is just undeniable. The entire AI revolution as we know it is being built and is running on NVIDIA's silicon. The only question is, for how much longer?